Okay, good evening, everyone. So we will continue to discuss for the fundamental of metal oxide semiconductor field effect transistor. So on Monday, we have to talk about the issues that in the case with the CV characteristic, one of the main purpose we do the CV is we want to characterize the fixed charge, especially related to the fixed oxide charge. So we can see from the CV curve, it's already see if once our CV is shifting to the left, and based on this flat band voltage equation, so we can realize that the increase of QSS can cause the decrease of a flat band voltage. So then we can realize that the CV is a very useful tool to help us to determine the equilibrium fixed oxide charge. And another very useful way that the CV can help is that this CV can help us to analyze the interface charging effect. So as we already mentioned that this is silicon and this is silicon dioxide. So in anyhow, our silicon will be terminated in the somewhere, and this termination of the top surface that will in the end to have a lot of allow interface state or allow energy state in this forbidden gate region. So this allow energy state in the interface, so that's why we call this as an interface state, as shown here. And once we give the bias on our metal side, in the end we can create the electrons at the surface, and then the electron can have a chance start to jump into this interface state, and that will cause electron trapping. And the same things can be happen for if we have the holes generations at the surface, and then the holes can also have the chance to jump to this interface state, and that will cause hole trapping. So in anyhow, the charge can flow between the semiconductor and interface state, and that will cause very serious trapping issues. And in the end, this will become one of the major reliability issues in every semiconductor. No matter what kind of semiconductor you are working on, you might be working in the silicon base, 3-5, 2D, whatever, every semiconductor technology always suffer reliability issues. Okay, so let's go for further to understand some more details related to interface state. Especially in here, I want to specifically mention about the acceptor state and donor state. So we have the definition that the acceptor state exists in the upper half of the band gap, and then the donor state exists in the lower half of the band gap. So, and in this case, we have the two situations. One is, you can see this is a acceptor-like interface state, and this is a donor-like interface state. So, the acceptor state is neutral if the Fermi level is below the state. So then we can see the case like here. This is our state. If the state is neutral, that means the states are not being charged with any charge inside this state. And then if this state is above, if the Fermi level, this is our Fermi level, if the Fermi level is below this state, then we can consider this is a neutral. But if our EF is larger than our state, and this will become negatively charged if the EF is above the state. So that's pretty important. That gives us some of the information related to what kind of state being charged or not in the case of our EF position. So we can usually characterize our state with a certain energy level. That's how we call the ET, where T means the trap. So in this case, is first one is EF below ET. Then we don't have any trapping happen in this acceptor state. But in the case with EF larger than ET, then we can start to have this negative charge inside this state. So that's the basic definition for the acceptor state. And on the other hand, we have a similarly for the donor-like. And donor-like has a opposite definition compared to the acceptor. So donor-like is a donor state is neutral if the Fermi level is above the state. So that means if we have the ET, that's our trap, our interface state, energy level, ET. And then if our EF is larger than ET, then actually in this case, the donor-like state will behave as a neutral, as shown here. But on the other hand, if the Fermi level is below the state, then we will have the positively charged, which is shown in this graph, where our EF is smaller than ET. So where our EF is smaller than ET. So in this case, that we have the donor-like state will behave as a positive charge. So now we can realize that in the previous lecture, we already mentioned that the EF, if you try to look at when we talk about the bias, if you look at the CV curve, we analyze the Venn diagram, we already show that actually the EF is correlate with our gate bias. So that means the charging of this interface state is also highly correlated with our gate bias. So the charge of interface state is a function of the gate voltage applied across the capacitors. So then if you look at this previous Venn diagram, let me just try to find like here. So you can see under the gate bias, then you can see at this moment our EF is actually, if you consider the different case, this is a case we start to have an inversion. So that means now this state below, if this state below are acceptor state, then we'll start to be in charge as a negative, because now this state is below our EF. So we can understand this EF, especially in here, because in here is also related to sometimes we have a Venn diagram as a flat. We have a Venn diagram as like this way, or we have a Venn diagram like this way. So then imagine in this position, actually the state is sometimes below EF, sometimes above EF, right? Because under the different situation of band bending, this EF will sometimes below certain ET, sometimes above certain ET. So that's also consistent with what we have been mentioned, that if we have electron here, then electron will be able to jump to here and trap in this place, because right now our ET is below our EF. So try to think about this. So in anyhow, everything is very consistent. Just you need to try to get used to the concept that the state sometimes below EF or above EF, and then once below EF in the case of acceptor state, then we start to have a trapping. So that's the purpose why we have specifically mentioned this here. So this also in the end give us some result that can cause our VTH shift. So for example, if you look at the IDVG characteristic, as I say that in the end we want to correlate every physics concept with our most important, the transistor characteristic. So we always will be interested to understand how this state charging that will influence our IV characteristic. So if you look at for the IDVG, where is the current versus the voltage, drain current versus voltage. In the beginning, we have this fresh curve. That's a threshold voltage, right? But now, if this in the case that we have the acceptor-like state, which means that we have the negative charges being trapped in the interface state. And then in this case, we will start to see the threshold voltage shift to the right. And this is because we have a negative charge in the acceptor state. So that's, in general, we can consider this is electron trapping. And the same, if we consider for the donor-like. So the donor-like means that once our EF below our ET, then we will still start to have the positive charge. And the positive charge will cause our threshold voltage shift to the right. So then we have this VTH here. Then this is, we have the positive charge in the donor state. So that's as a whole trapping. So that's a main implication in the later to for the analysis on our transistor, how this interface state charging will influence our device characteristic. Okay, so then again, this is a Venn diagram where I just mentioned that in the case of a Mi gap here, then our EF is in the middle. But now if we apply the positive gate bias, so during the positive gate bias, you will try to pull this banding. Then you will actually have a more interface state below our Fermi energy. So this is a one start being trapping as a negative acceptor. So this is because of at this moment we have a more acceptor trap, acceptor state below our EF. And similarly, the same in the accumulation where we bias at the minus VG. where we bias at the minus VG, and then we have the positive donor star will be on our EF. So where is EF? This is EF. Larger than EF is smaller than ET. So now our EF smaller than ET, then based on the definition of the donor state, we will start to have the positive charge here. So this is a case under the positive of the negative gate bias in the end will cause a trapping in the positive gate bias, because our EF is star above our ET, then we have the negative charges here. But in the case with the EF smaller than ET, we start to have the positive charges here. So in the end, with considering this interface, then we will have the stretch of our CV curve. So ideally, we have a CV curve in this way, but with considering this interface state, then we will see the CV have this kind of the change, which we call as a stretch. So this is everything that what the CV curve can help us to identify. If we see the flatband voltage shift, then we know there's a fixed charge that influences our CV characteristic. If we see the stretch of this CV curve compared to this ideal one, then we know there's some influence coming from the interface states. Okay, so finally we finish the CV, then we will start to move for the transistor, which is MOSFET. So in the case of MOSFET, we have mentioned many times related to MOSFET. Finally, we will move to this one to really understand that what would be the operation of the MOS transistor. So in the case of MOSFET, we can divide by several different categories. The first one is what we call the N-channel enhancement MOSFET. And also we have another case is N-channel depletion MOSFET. So the difference between the enhancement mode and the depletion mode, which is based on the threshold voltage difference. In the case of the enhancement mode, threshold voltage is larger than 0. But in the case of the depletion mode, the threshold voltage is smaller than 0. So in this case, for example, in the enhancement mode device, we need to have the VG, we have a threshold voltage here. But once we have the VG larger than VTH, then we can start to have the electrons inversions in the channel. But at the meantime, because the MOSFET is a 3-terminal device, which we will bias the source as a ground, but we will also bias the VD here. And we have the positive VD, we have a negative electron. So now we can foresee the electrons will try to flow from left to the right. So this is our electron flow. And the electron flow is just in the opposite direction of the current. So which means the current is in this direction. So that's the direction for the current flow. So then we can sense the drain current from the drain side. So in this case, if you try to plot the IDVG curve, right now, because of our threshold voltage is larger than 0, so that means if we try to sweep the VG from small to large until the VTH, the VG is larger than VTH, we can start to see the current. We can start to see the drain current. So that's a basic characteristic for the N-channel enhancement MOSFET. And the same if we consider in the case with N-channel depletion mode. The main difference is that in the case of depletion mode, you already have the N-channel that's already existing. So the N-channel is already existed. And then even without any bias, we already have a channel. So even without any bias, we already have the electrons below the gate. So then the next question is that we don't apply bias, but we already have a channel. So it's good for turn on of the transistor. But another consideration is that how do we switch off our channel? Because in the left hand side, this enhancer mode device is that in the beginning we don't have a channel, so we have to apply the party bias to induce the electrons. But in the right hand side, the channel is already existing. So then the next stage is that we need to apply a minus VG is needed to turn off the channel. So in this case, we apply the VG negative bias is needed to deplete the electrons channel. So what does mean the deplete here? It just you have lots of electrons here. Then you have to apply the negative bias. Try to push these electrons away. So that's why we have to call this as a negative bias to deplete, because we want to use this negative bias to push these electrons are far away from the channel. So because of this deplete the channel, so we can turn off. And because we need to deplete the channel, that's why we call this as a depletion mode. So that's why this is we call as a N-channel depletion mode device. So now if you look at the typical IDVG characteristic, So first of all, at the 0 volt, without any bias, we already have the electrons in the channel. So that means at the 0 volt, we have the currents. Now we start to apply the negative gate bias until enough negative bias. We can start to push away the electron in the channel, and finally we can deplete the channel. Once we deplete the channel, then we can switch our device to the off state. So then our device doesn't have the current anymore. So the same, we define this one as what we call as a threshold voltage. So that's why in the case of depletion mode, the threshold voltage is below 0, which is the negative values here. Compared to the enhancement mode, the reason why we call it enhanced because of the electrons in the channel is given the positive bias to enhance the channel carrier. So that's why we call the enhancement mode device. And compared for the real practical consideration, the enhancement mode device is more popular being used in the most of the application, and only very few cases that we use the depletion mode. That's for the silicon, but for 3-5 or compound, we are very often to use the depletion mode device. But that's another story. Just try to compare these two devices on this slide. Then the N-channel enhancement mode is the one that the most popular use. So we have the N-channel enhancement mode, depletion mode. So also the same, we will have the P-channel enhancement mode and the depletion mode as well. So in the case of a P-channel, what we need is to apply the negative gate bias, because right now we have the N-type substrate, so we need to apply the negative gate bias to induce the holes in the channel. So this is the case of the P-channel enhancement mode MOSFET. So in this case, if you look at for the IDVG, so we have to first to apply at the 0 volt, there's no current. Because of this is there's no holes yet in the channel, so at the 0 volt there's no current. So we need to start to apply the negative VG until the enough negative value. We start to induce the holes in the channel. So in this case, we have the threshold voltage at here. So this is our enhancement mode P-channel device. And the same, we can have the P-channel depletion mode. which the holes are already existing in the channel. So you can see this is a P channel. That means the holes are already existing. So what we need to do is we have to think about the one way to deplete our holes. And because we have a positive charge in the channel, so the only way to deplete, to push away the holes is that we need to apply the positive gate bias, right? So in this case, positive gate bias is needed to turn off the channel. So then if you look at the IDVG characteristic at 0 volt, the channel is already there, the holes are already there. So at 0 volt, we have the current. But now what we need to do is to increase the bias beyond certain point. Then finally, we can push away our holes in the channel and then to switch off our device characteristic. So in this case, this is our threshold voltage. So this is a case of a depletion mode, P channel MOSFET. And then if you compare these two, for sure, the P-channel enhancement mode MOSFET still the main one we use in the most of the application now. But still, you need to understand there's a difference between the enhancement mode and the depletion mode. Okay, so now we have the physics-based understanding for the MOSFET operation. So we have already briefly to talk about what actually the way to form the MOSFET transistor and what would be the typical IDVG characteristic look like. But now we are getting more serious, try to help you to understand the current voltage relationships here. So now we consider N-channel enhancement MOSFET with a gate source voltage that is less than threshold voltage and with only very small drain to source voltage. So in the first consideration, what we consider is our VGS smaller than our threshold voltage, and also we only apply the small VDS here. So, and then as usual, the source and the substrate are at the grounded. So we will ground the source, we will ground and the substrate here. And with this bias condition, for sure, there's no electron current, there's no electron inversion layer. There is no electron inversion layer because at this moment, we bias at the Vg is smaller than Vt, and then for sure at this moment, there won't be any electrons in the channel. But there's one particular thing have to mention is that we try to apply the small VDS and think about this PN junction. As I previously already mentioned that the purpose to understand the PN junction is not only for the PN diode, but also it's very crucial in the end to understand the MOSFET operation. So we have the PN junction here. So that means if we only, although we might apply small VDS, but still this small VDS in the end will have the reverse bias. So we will have the reverse bias. So this small VDS will create the reverse bias of this drain to substrate PN junction. And then with a basic understanding of the reverse bias, once we have reverse bias, that means we have the depletion region is slightly larger than at the zero bias. So that means we should foresee there's a depletion region at this P and N junction interface. But because of this is a small bias, so now we can expect that this depletion region is not that large. So we have the depletion region. This is our depletion region. The next phase is that we will start to increase our gate bias. And once we increase our gate bias, when we have the VGS is larger than threshold voltage, still we apply the same VDS here. Because of now we apply Vg is larger than Vt, we can expect an electron inversion layer can be formed under the channel as shown here. Induced electron inversion layer. So electron inversion layer has been created so that when a small drain voltage is applied, the electron in the inversion layer will flow from the source to the positive drain terminal. From the source to the positive drain terminal. We apply the VGS larger than threshold voltage, so then we can have the inverse electrons in the channel, and because now we apply this VDS, so then this one electron flow can flow from the source to the drain. This is electron flow. So that's why we start to see the drain current. And in the ideal case, we assume there's no current through the gate terminal. So in the ideal case, we assume this gate current is equal to 0. But of course, in reality, based on the the tunneling, quantum mechanics tunneling, we can always have a gate current. But now to simplify this, we consider the Ig is equal to 0. So with considering, there's also one thing I want to mention, that this is actually the space charge region that I draw here. This is our space charge region. And the space charge region here is due to the reverse bias of the drain to substrate PN junction. So when we consider a small VDS value, the channel region has the characteristic of a resistor where our drain current is equal to our GD times VDS, and then the GD is defined as a channel conductance, which is inverse proportional to our resistance. So for smaller VDS, the channel region has a characteristic as linear, whereas that our drain current is a positive correlation with our VDS with a consideration of the GD, which GD is the channel conductance, and then the channel conductance is also has a positive correlation with our QM, which is our charge, our channel carrier, which is related to our channel carrier here. So we consider the small VDS, which we have ID, VD, and then we will have the, in this case, because our current is linear proportional to our VDS, so then we can expect our current is like in this way, with a case of our VGS1 larger than VT. But also our conductance, channel conductance is proportional to our the carrier, the charge that can be induced in the charge that can be induced in the inversion channel. So that means if you look at the simple MOSFET schematic, so we apply the first case where our VGS1 larger than VT, then we can have the inversion charges in the channel. That's due to our electron inversion. But now, if we consider the second case, still we have the source, drain, oxide, and metal. But now our VGS2 is larger than VGS1, is larger than VT. So higher gate bias, for sure that we can expect our channel charge, our channel carrier is increased, our inversion, our electron concentration in the channel is increased. So we can expect a higher concentration, higher electron concentration in the channel. So in this case, our IDVD is become like this way, where our VGS2 is larger than VGS1. Right? And the same, if we have a VGS3 larger than VGS2, we can have this higher current, and now our current is only linear proportional to our drain bias here. So the inversion layer charge is a function of gate voltage. Therefore, the basic MOS transistor action is the modulation of the channel conductance by the gate voltage, where our mu1 is the mobility of the electron in the inversion layer, and the Q1 is the magnitude of the inversion layer charge per unit area. So this one is proportional to our gate voltage. So then, in this case, with a smaller VDS, we have this typical IV characteristic, especially this is ID, to be more precisely, this is IDVDS. So again, if we try to drop out all this, and then that would be the next line. This is the case when our VGS larger than VT and apply VDS is small. So in this case, because our VDS is small, so then the depletion region in the drain side in this reverse PN junction doesn't influence our charge in the channel. So now we have this uniform channel under the gate oxide region. So with a small VDS, we have an electron flow to the right, also equal to the drain current flow to the left, and we have this linear characteristic. Of course, what we actually want to understand should not be only limited in the case with a smaller VDS. So then the next phase, what we want to discuss is in the case if we keep increasing the VDS, and what happens. When the VDS value is increased, then actually the voltage drop across the oxide near the drain terminal decrease. This is because if you consider the voltage difference between the gate to drain side, which is VGD, is equal to VGS minus VDS. So now if we increase VDS, then we will have the decrease of the VGD. So once we have a decrease of our VGD, that means the induced inversion charge density near the drain side also decreases. Right? Because the charge under the gate is always positive correlated with our gate bias. And now because our VDS increase, so the voltage at this point, VGD is actually decreased. And this decrease means the induced charge here is decreased as well. And therefore, we can start to foresee the induced inversion charge here decrease also means our IV curve, our current, the slope of our current will decrease. The incremental conductance of channel at the drain decreases, which then means the slope of ID versus VD will decrease as well. So what does this mean? This means if we look at the IV, ID, VD characteristic, ID, IDS, VDS characteristic, then in the last slide we have mentioned in the beginning with a smaller VDS we have a linear correlation, but now because of the VGD decrease, so then the inversion charges here decrease. Then if our inversion charges here decrease, suggests that our channel conductance decreases as well. So the channel conductance decrease suggests that our slope of current increase will decrease. So therefore we can start to see the slope decreases. This is because our conductance decrease. So this is the meaning of this sentence. So now we can understand that once we increase VDS, we cannot have the linear increase of our drain current. But in the end, we start to see the decrease the slope to a certain point. So that's issues mainly come from that we start to have the higher drain bias, and that cause the higher drain bias will lead to the lower gate to drain voltage and decrease our carrier and conductance in the drain side. So then we don't have the uniform inversion charges anymore. We have this decrease of the inversion charges toward the drain side. And then if we continue to increase the VDS, then we will reach the one condition that at this moment, because right now VGS minus VDS, which is equal to VGD. If we keep increase VDS, and then our VGD will continue decrease to the point equal to threshold voltage. So if at this bias point our voltage is equal to threshold voltage, that suggests that our inversion carriers here become 0, right? Because of we already mentioned the threshold is a criteria. Beyond threshold, we start to have the inversion charge. Below threshold, we don't have the inversion charge. So once we increase the VD, then once we increase the VDS, then our VGD will continuously decrease to the point that can be possible below our threshold voltage. Once below our threshold voltage, then we don't have any inversion charge in the general in the drain side anymore. And then at this condition, we call as a saturation, VDS set, which is this one. So when VDS increase to the point where the potential drop across the oxide at the drain terminal is equal to VT, the induced inversion charge density is 0. At the drain terminal. So therefore, if you look at our IDVD characteristic, we will start to have this kind of a characteristic where drain current versus VDS, and as already mentioned in the beginning, we have the linear increase, but then we decrease the slope. But at one moment beyond at this, there will be the moment that we don't have any inversion charge at the drain side, and this is a moment we call as a VDS set. Why we call the set here? This is because of beyond this region, we call as a saturation region. And before this condition, we call the linear region. But now we still don't know yet what happens after this region, right? Because we just know that at this moment, there's no inversion charges at the drain side. So, but we don't know what happens if we continue to increase the bias, the drain bias beyond this VD set. Do we still have the current or not? Because at this moment, we already have the 0 charge. But now, if we keep increasing VDS, do we still have the current or not? So this is an issue we are going to discuss in the next slide. So in the case of the keep increasing, in the case of a keep increasing our VDS, when VDS become larger than VDS set value, the point in the channel at which inversion charge is just 0 move towards the source terminal. So what does this mean? This means that if you look at the charge formation in the channel, we have this one, and we have this. Because right now we consider our VDS is larger than VDS set. And once we continuously increase our drain bias, actually we start to increase our reverse bias of our PN junction, which, if we plot the graph here, where we have the source, we have the drain, and we have the P-type substrate, and we have the gate. Now we continuous increase VDS larger than VDS set. That means we increase the reverse bias of this PN junction. So increase reverse bias means our depletion region is getting wider and wider. So that means we have the large depletion region, which is the space charge region here. And this also will try to push our channel far away from the drain side, because this depletion region. So now our channels in the our electrons in the channel will become this way. So again, just let me illustrate again. This is the case where our VDS is larger than our VDS set, and we give the high bias to reverse bias this PN junction, and then our depletion region is increased, and this depletion region increase will in the end to push the inversion layer start being far away from the drain side and become like in this case as shown here. But now the question is that if we still have the VDS and we still have the VG, so because we still have the positive bias here, so the electrons in the source side will first still flow to this channel region. But how do they reach to the drain side? Because we have the huge depletion region here. But then we need to consider back to the understanding of our PN junction. Inside this depletion region, actually we have the electric field in this direction. So the electric field in this direction will help this carrier here sweep to the drain side. So the carrier will be helped by this electric field to reach to the drain side, in the end to become as a current that we can collect from the drain terminal here. So in the case electron enter the channel and the source travels through the channel toward the drain, then at the point where the charges go to zero, the electrons are injected into the space charge region, which is this one. I should indicate in here. So the charge will inject into the space charge region and start this charge will be swept by the electric field. To the drain terminal. So this is the process that I'm saying here. So this is a case that the VDS smaller than, I just write it small here. This is VDS larger than VDS set. And back to this schematic, we are using the same knowledge here. So still, because right now VDS is larger than VDS set, so now we have the inversion electrons as shown in here. We have the inversion electron like in this way, and now we have the electrons from the source will first to flow to this inversion layer, and then because of this space charge region, so we have the electric field here. And with the help of this electric field, so now our electron can reach to the drain side and become as a current here. So that's the last part of our MOSFET operation under the high drain bias. So again, we can complete the last picture for our IDVD, where we have the drain IDVD curve. So we already knew that in the beginning we have linear, start to saturate, reach the one particular point, and we call this point as a VD set. And beyond this region, we will start to have the saturation current here. Thus we call this as a saturation region, and this as a linear region. And then the channel, the electrons in the channel can be schematically drawn. In the beginning we have a uniform channel, and once we start to increase the drain bias, and then the voltage drop in the drain side decrease, so we have uniform become this trapezoidal, and once to reach to the certain point become this triangular. And then in the saturation region, our inversion charges in the channel is become like in this way. So this is a physics-based understanding for the IDVD from the small VD, medium VD, and large VD in the end to reach to the saturation region. So finally, we can complete this full IDVD curve. We have the IDVD and we have the current is shown here, but this is only at the 1 VG, but for sure we will continue to increase the VG. So if we increase the VG, VGS here. Then we will have the curve so this is IDVD at a different VG, and then we can always define as a one point which reach to the saturation point, and this is one as a VDS saturation is equal to VGS minus VT. And we can divide this graph by the two regions. The left hand side is we call the linear region, and the right hand side is we call the saturation region. So in the case with a non-saturation region, or we call more generally we call as a linear region, then we have the current equation as shown here, where drain current is equal to L channel width mobility Cox and 2 times VGS minus VT VDS minus VDS squared. So that's the current equation we have in the linear region. And also in the case with the saturation region, we have the current equation. Drain current is equal to VGS minus VT 2 as shown here. So that's an analytical equation to describe the current in the linear or the saturation region. And since we have the physics-based understanding, now we show the current equation in the linear and saturation region. Then for sure the next stage, we're going to derive this equation. So with considering for this equation, we have some following assumptions. The first one is that the current in the channel is due to the drift rather than diffusion. And second, there's no current through the gate oxide. And third one, a gradual channel approximation used in this case. This approximation means that the EX, electric field in the X direction, is a constant. And any fixed oxide charge is an equilibrium charge density at the oxide semiconductor interface. And then the carrier mobility in the channel is constant as well. So now we are going to do the step-by-step to derive this current equation. So first of all, we're starting from the general Ohm's law, where our current Jx is equal to Ex times our sigma here. And then from this schematic, we can see we have the W and L, which W is channel width, and then L is a channel length. So the current in the Ix is equal to, we have an integration of a current versus dy dz, and we have a charge distribution, and in the end we have this current equation is equal to with mobility or magnitude of the charges in the channel, and then the electric field in the x directions. Now we have to apply again for our charge distribution. First of all, because we still have to consider the charge neutrality, where our Qm, this is under the positive gate bias, so that's why we have the positive charge in the metal, our fixed oxide charge, and then our inversion charge, and also our depletion region charge. Everything should be equal to 0. And also we apply the Gauss law. We consider this Gauss law where our Qt is total charge enclosed by this surface, and En is the outward direct normal component of electric field across in the surface phi here, and surface 4 is only the surface that contribute. So in the end, we can have this one. This is the equation we already showed before, equals to Qt. And also Qt is equal to here, this one, minus this one. In the end will become this. So that's the Q. So Qt is here. Qt is here. So will be, in the end, we can follow the Gauss law to further derive. So again, we consider for this calculation, then the first one, we try to estimate the EFP minus EFN. EFP minus EFN will be equal to VGS minus VX. And VGS minus VX can be seen from here, which is this one. Then we have the VGS minus VX is equal to Vx plus 2 phi FP plus phi ms, and where phi s is metal work function and phi s equal to 2 phi p is the consideration of the inversion condition. And we have electric field is equal to V over thickness. And therefore, this one can be further considered as here, because this is Vox, so we can put this here. So this one is equal to this one. And then, where the Qn plumb here is also equal to this one. And then in the end, we will have this current equation. In here, I won't go very detailed because I think everyone who read the textbook step by step, you can understand this equation calculation, because the most purpose is still the physics base to understand the current operation. So then, with all these equations, with considering the total current in the channel length, so we integrate from 0 to L with this equation, and because now the drain current is equal to minus Ix, that's just due to the coordination issues, with considering the VGS larger than threshold voltage, and also VDS is below VDS set. So we have the ID. Finally, the ID is equal to this one. But if you try to plot this equation, then you will find out that actually this equation will exhibit like in this way. The equation will exhibit like in this. The equation will exhibit like in this. So that means at the VDS at the peak current value, then we will have this derivative equal to 0 and VDS equal to VGS minus T, and therefore this will cause that revise this equation in the end become, first of all, we have this up to the peak, and after the peak, which is our saturation region. Then we have this, where ID set is equal to so now we have this saturation equation, saturation current equations. So finally, physically, we are understanding what would be the cause for the linear region, what would be the cause lead to the saturation region, and also we have this equation to support our understanding. So with this, with considering this equation at a case with a smaller VDS, we can reform the equation shown here, which in the end will be equal to this one. So that means if we try to plot the ID VGS, then we have this slope. It's equal to this one. And if we try to plot this versus this, then we can also have this slope here. So the extrapolation of the straight line to the zero current gives the threshold voltage, and the slope is proportional to our inversion carrier mobility. So that's just a kind of a way that we reuse this equation, allow us to extrapolate the channel mobility and then the threshold voltage. So the same in the case of the p-channel device, we have exactly the same equation. ID is equal to 2LW, but now we have to consider the whole mobility in the channel oxide capacitance. But now we have to consider VSG, because now we have VSG here and VSD here. So that would be VSG minus VT times VSD. So that's our current equation for the P channel. And the same, we have the saturation, which is exactly the same like the previous derived saturation for the N MOSFET, where we have a W. Now we just replace as a whole mobility over 2L VSG minus VT here. So that's our saturation and linear current equations. So here I just provide very simple equation, a simple example that how we use this equation. So basically, this is an example that we try to design a width of MOSFET that the specific current is induced for the given applied bias, and consider an ideal N-channel MOSFET with a parameter of a 1.25 micrometer, mobility 650, CRs 6.9 times 10 to minus 8, and threshold voltage 0.65 volt. So we want to design the channel width that can reach for the 4 milliamp for the saturation current at the VGS 5 volt. Although the equation, the example here is very simple, but actually it's very useful, because in the future, why we have to use this equation, because why we have to learn this equation, because in the end, we want to use this equation to help us to design our transistor. Of course, in nowadays, we are barely use the hand calculation to derive, to design our transistor. We mainly use the TK, some software help us to design the transistor. But in the case of TK, they are running the same things. They're using the exactly same equation, same physics. Just it's calculated by the computer rather than by ourselves. But anyhow, the mindset is the same, all based on the same equation. Where first of all, look at for the saturation current, where we have ID saturation is equal to this one. We have the width, electron mobility, oxide thickness, 2L, and we have a VGS minus VT square here. So then, in this case, what we actually want to have is a design the channel width that can achieve for such transistor performance target, where we want to have the 4 milliamp at this point, and our channel length is 1.25 micrometer, and we have mobility of the 650. We have a CRs of the 6.9 times 10 to minus 8, and we want to bias this one at the 5 volt, and then the threshold voltage is equal to 0.65 volt. So now you can see that this is a very simple design equation, simple question for design the transistor based on this saturation current equation. Then with this parameter, so we can have the width should be 11.8 micrometer. So this is a particular useful information, because in real device fabrication, when we try to design the transistor, we are not actually consider only the structure here. We are not only consider the case as shown, where we have the source and drain. In the previous, we only draw as a 2D schematic, as shown in here. We only draw the 2D schematic. But in reality, the transistors is fabricated with a 3D structure where we have the width in these directions. So actually the question here for calculation is very simple, but the implication is crucial, because this question is actually try to ask that in the case with this consideration with our channel length 1.25 micrometer, what is exactly the width we need to design for our transistor? But once you once you had a chance in the phase to design the transistor, no matter for your own fabrication or you tape out that somebody help you to make it, what we actually provide to them is not this schematic. What we actually provide to them is only the layout of this transistor, where we provide the layout that being looked at from the top view. So if we look from the top, then actually the information that we try to use to, no matter for the make the mask that in the end you need to fabricate transistor, or you need to provide this information to somebody else. So in the end, if you look at this view from the top, the information what you need to provide as a kind of the square like this one, and this is our width, and this is our gate pad. And for sure, beside to the gate, we have the source and drain. So we have the source here. So that's actually the real information that you will provide that for the fabrication purpose, that you need to design what we usually call this as a layout. So again, all I want to illustrate that for me, when we try to understand the semiconductor, the physics is always the first priority. Of course, to support the physics, we need to have the equation, but sometimes we are easily confused the calculation coming from this equation or what we should do on this equation. But this is one example that the equation here, we don't need a very sophisticated equation. We can use this simple equation in the end to design the transistor, what kind of width here to have the targeting drain current. So this is one practical example that we are doing the design day and night in the semiconductor field. Of course, the reason that once in the future you really design a transistor, you seldom use a hand calculator is because of what we need to design the transistor is way too complicated than this one. And sometimes the one thing, there are too many parameters need to consider. We are not only optimize the width, we need to optimize the channel length, we need to consider the different oxide width, we need to consider the contact resistance. This all makes this design become more complicated. And second is that for the very advanced semiconductor device, sometimes we are lacking of this very precise equation. So in the end, we have to rely on the TK, some software to help us find the best and optimize the parameter that can fit our goal. Okay, so with considering the the basic MOSFET operation, there's some additional parameters that we are used very often. We are not only take interested in the IDVG, but also we are interested in something else, especially in here we call as a transconductance. So the transconductor is defined as a change. How we define transconductor is we have the GM is equal to the derivative of the drain current versus the derivative of the gate voltage. So transconductor is defined as a change in the drain current versus the change in the gate voltage. So in the end, actually, when you try to calculate transconductance, actually from the IDVG curve, where we have this typical IDVG, but once we try to estimate the transconductance, which is a derivative of the drain current versus the gate, that means our transconductance plot, our GM versus VG will become this one, because the derivative of the current versus the VG, this actually is the same calculation of the slope, right? If you try to think about this calculation, what we really calculate is each small VG, we want to look at the increase of the drain current. Each small VG, we want to look at the increase of drain current. So in the end, the transconductance is trying to calculate the slope of each one. And why we have this peak? The peak is happening at the peak increase of our drain current, so it should be somewhere in this region. Because after this peak increase, the slope is decreased. So that's why you will see the slope decrease. So then the real calculation for the real meaning for the calculation for transconductor is actually we want to estimate the slope for each small increase VG versus the corresponding drain current here. And also, this slope sometimes referred to as a transistor gain here. So that means actually if you try to look the IDVD, so we already knew the IDVD should be plotted in this way. But actually, the IDVD is, each IDVD is a 1 VG, based on the 1 VG. So this is a VG0, VG1, VG2, VG3, right? And then each VG gives us a 1 ID0, ID1, ID2, ID3. So then the calculation with this one, ID1 minus ID0, over VG1 minus VG0. This is exactly the same like this one, right? And that means actually we are here to calculate the transconductance 1. And where is the transconductance GN1? It's actually here. So that's why we call this transconductor as a transistor gain, because we want to understand how high the current gain can be achieved if we increase the gate voltage here. So now we have the GN1 here, GN2 here, and GN3 here. And the one general issue that we already see here from IDVG, you can see the slope is decreased. The slope decrease, that means your transconductance decrease. The transconductance decrease suggests that beyond certain critical bias, maximum bias, if you want to increase the gate voltage further, actually your current gain is increased very small. So this is GM4. And the increase amount for this last one, which is related to GM4, is because now with a high gate bias, our GN is decreased. And this is very important for the certain device or even the circuit operation, because for the device and circuit operation, we always want to operate in the region that has a very high gain. So that means we want to bias at this region, because we bias at this region, that gives us the most largest gain that for this transistor under the operation. So that's why this refers to the transistor gain. So the transconductance, to be honest, is not a new concept. It just calculates slope IDVG, and we can already see the transconductance inside the IDVD as well. And of course, we can further to calculate the transconductance in the non-saturation region, in linear region, which will be equal to this one. This will be equal to this one. And some of the additional concept is also very important, is that we need to consider the substrate bias effect. And sometimes we call this as a body effect. So in most of the case, we try to ground the substrate as a 0 volt, just like the source. But in some consideration, actually, the body, the substrate might not be the same bias as the same bias as a 0 to the source. So therefore, if the VSB is larger than 0, then actually we have to reconsider our band diagram, where under the threshold inversion condition, we have the phi s is equal to 25p. But now, due to additional bias coming from the substrate, so therefore, the E phi s is equal to E 2 phi fp plus VSB here. and the VSB is due to the bias in the substrate. So when substrate VSB is larger than 0, the service will try to invert when phi s equal to 2πp. However, these electrons are at higher potential energy than other electrons in the source. The newly created electron will move laterally and flow out of the source terminal. And in here, the explanation here, the text here is not that important. Most important is that we need to understand there will be the issue that are coming from the substrate, and then that will be cause the difference in our threshold voltage value, because due to the substrate bias here. So that's why in most of the case we would like to make this as a grounding, because then we can eliminate these issues. But still there's some consideration that it might happen that the VSB is not equal to 0. And if the VSB is not equal to 0, then everything what we calculated before, we have to recalculate again, because we have a phi fp here. Then the phi fp have to reconsider as 2 phi fp plus VSB. So the every equation what we have to replace the 2 phi fp as a 2 phi fp plus VSB. And in the end, we can estimate the threshold voltage difference between with substrate bias versus no substrate bias. So therefore, we have the what we call the body effect coefficient gamma here. With this gamma, then we have this delta VT is equal to this one. So then let's talk about one of the application for the MOSFET is that we need to make it as a CMOS, which is a complementary MOS, or we just call the CMOS. And we actually already mentioned the purpose for the complementary MOS or CMOS is that we would like to fabricate the PMOS with NMOS together, and we are connecting with the same input and output, which is a PMOS versus a MOSFET. And then the purpose to have this PMOS and NMOS being connected is in the end we want to have the function that logic function that we call the inverter. So in the case of inverter, once we give the logic signal as a 1, we will have the output signal as a 0. If we give the input signal as a 0, we have an output signal as a 1. So that's the purpose for the CMOS inverter. So to realize inverter, we need to fabricate the PMOS and NMOS side by side together. So there are several possibilities. Just like this one, we have a P-type substrate, we have an N well. So therefore, in this case, we have a PMOS here. We have an NMOS here. So that's one possibility. And also we can consider using the N substrate, where we need to have a P well to form the NMOS, and then the PMOS can have directly on the P substrate, on the N substrate. Or we can both have a P well, N well together. So we have NMOS, PMOS here. So this is a basic for the CMOS inverter. So that's why the purpose we learn the MOSFET. Of course, there are many applications on MOSFET, but the CMOS is one of the most important one. And here is some more detail for the CMOS technology here. So if we consider this one where we have a PMOS and NMOS here, so we can make us a circuit symbol as shown here. And as I say, we will connect these together as a single input and single output. So that will be V in. This will be V out here. And for this PMOS, we have the gate, source, drain. And for the NMOS here, we have the gate, we have a drain, we have a source here. So the operation for the inverter is basically like in this way, that we to have the inverter function, what we actually want is we give us one input signal V in. And if we have the one input signal as shown in here, and then for our V out, we'll have the output function, because this is inverter function. So the input high means the input is 1, and then we will have the output as a low, which is a 0. So then we can realize this output waveform in here. So that's a inverter from the input and output. So we will actually be able to realize the detailed operation for for CMOS. You can find for the many the online material or even the textbook. But the general idea is that if we apply V in, if it's larger than VGS of the threshold voltage for the bottom NMOS FET here. So then in this case, our NMOS will turn on. So once our NMOS FET turn on, so this will turn on, this will off at the V in high, which is V in larger than VTH. So then you have a current flow in here. So that means we can start to have a V out. It's a signal. And then the V out will be roughly the same, close to the VGND ground, which is depends on our resistance here. So NMOS turn on. So this will lead to our V out will approach to our VGND. So that's why we get it as an inverter function, because we can consider the high V in as a 1, and our output is close, is approach to the ground. So that would be considered as a 0. So then we have a 1, 0. So this is in the case of the logic circuit, how they actually, in the logic circuit they only have the 0, 1, 0, 1, but how do they have 0, 1, 0, 1 is because they consider the high voltage as a 1, low voltage as a 0. So finally, we consider this MOS transistor. This is one reference just for your have some information up to date that what would be the current technology can be made. So what the textbook is mentioned is, to be honest, are very, very old technology. Everything on the textbook, to be honest, is a technology that we are not using now, and it's also not the technology that we are developing in the future. But of course, those knowledge in the textbook are very classical and epic that everyone should have to have the fundamentals. But now we can start to look at that what would be the general status for the future transistor. So this is one example that paper published in the Nature that which use a 2D material to fabricate a transistor with a 1 nanometer channel length. So again, if you look at this, is a paper published in Nature, which is the highest, the most well-known journals in terms of in the scientific field. So again, if you look at how this paper organized, so we can find out that this one still the same will be the general background information. As I mentioned, the scaling of transistor is predicted to fail below 5 nanometer gate length because of the severe short channel effect. As an alternative to the silicon, certain layers semiconductors are attractive for their atomic uniformity thickness down to a monolayer, low dielectric constant, large band gap, and heavier carrier affecting mass. So this is a general information. Still, the beginning of the abstract of the one journal or academic article is always in the beginning with some background information. And in this paper, let's start to go for the main point here, where in here we demonstrate the MOS2 transistor with a 1 nanometer physical gate length using a single wall carbon nanotube as a gate electrode. So that's the main purpose of this, main motivation of this wall. And then you don't understand the MOS2 is fine, but we can still look up what actually want to demonstrate the characteristic in here. This ultra-short device exhibit excellent switching characteristic with a near idea of subthreshold swing of 65 millivolt per decade. So now, again, we come to the key information with the subthreshold swing. If you still remember that what we already mentioned in the last lecture, I say the best SS we can achieve should be the 60 millivolt per decade. That's the limitation for the semiconductor transistor. If we follow this kind of a switching operation, then 60 millivolt per decade is the limitation. So this wall, why this wall is worth reading? Because he demonstrates this transistor with a 1 nanometer channel length can still have the 65 millivolt per decade. So this is a paper to demonstrate transistor with 1 nanometer channel length. And then the first important characteristic, actually it's a one we already teach. So it's a one example that we learn the basic knowledge from this class. This is a very old knowledge that has been useful in the last several decades, but still quite useful now. The first one is the subthreshold swing. So in this paper, they demonstrate their device can have the very low SS down to 65 millivolt per decade. And also another one is that they demonstrate the very good on-off current ratio of the 10 to 6. So this is also the same some of the concept we already mentioned that if you still remember in the beginning, we already mentioned if you try to plug a log ID versus a VG, we will have the characteristic like this one. And then the subthreshold swing is calculated as here, where SS is equal to 60 millivolt per decade. But also another very important parameter that I have already described in the beginning is on-off current ratio. So here is I on, here is I off. So in this paper, let's say they can have on-off ratio of 10:6. So again, what we have been lecturing in this class in the end still are other very important parameters that every semiconductor professional paying a lot of attention on this. For example, SS for the on-off ratio, this and mobility, or so on, so on. And also, one more thing, the simulation shows that effective channel length here is 3.9 nanometer in the off state and 1 nanometer in the on state. So again, the concept of the channel length here. So in the end, even we don't look at the detail of how characteristic of this transistor look like, how do this look like, how do these transistors look like, and then how the characteristic look like. From the very short paragraph with just a few lines with introduction, we already knew the main information of this paper. The main information is that they have a 1 nanometer channel length device, they have a 65 millivolt per decade, they can reach the on-off ratio of 10:6. So again, if you look at this paper, you can find out that the same keyword that we use is all over again. So we have a however here, we have a finally here, we have nevertheless here. But in here, we don't go this detail, but we still already knew the main contents. So here is some characteristic for this 2D transistor with 1 nanometer channel length. But now you can see these are all the characteristics we are lecturing already. So this is a log ID, VG, and then what we care is a 60 millivolt per decade. And this is with a different VD. But one thing particularly, it's not that the critical concern, but still, as being the device engineer, we always pay a lot of attention for the threshold voltage, which is this one. So you can see now the threshold voltage is smaller than 0. So that means what I'm saying for the depletion mode transistor is not the only one existed in the textbook, but it's also the one that in reality people very often, occasionally to have. I would say in the real situation, we always want to have the VTH larger than 0 volt. But in this demonstration, the purpose is not to demo the very high threshold voltage. So people still feel that that's okay. That's just a demonstration for one channel length. So the threshold voltage below 0 volt is still okay. That means that if you want to turn off your device, you need to apply negative gate bias. You need to apply -3, -5 volt, as shown me here. And then this is their schematic here. So then this is a place where they have the smaller channel length here, LCH, that's equal to 1 nanometer. And this is a place they apply the gate electrode, which is VG. here. Okay, so finally, we finished the most lengthy part that related to the MOSFET. Of course, we still have some material still need to go, but on the MOSFET, but probably not today because it's already 8:30, almost like 9. So in the last moment, I just also want to mention that I still need to update again for the course schedule. So I apologize for this. Have to reschedule the course because in the end, because I don't want to make the final exam after our regular, because there's some of you might not be available after first week of June. So as we agreed last time, in the while ago, we agreed that we want to have final exam in the end of May. Of course, if you get finish the final exam earlier, then you have some more free time for the summer, for you have early of your summer vacation, you have early of your end of semester. But because of this, then we need to a little bit squeeze the schedule, and also some of the unpredicted duty from my side also need to rearrange the schedule. So let's look at the update schedule again. So this is one I show on Monday, but now I have to reschedule. So as I say, we are here. So first of all, I want to say that thank you all still stay with me until very late on the 9 p.m. today. And then I remember in one of the comments from the, for the midterm exam, we provide the additional score for every of you that you can provide a suggestion. And I remember that several of you mentioned that probably suggest me not to have the class on Monday morning, want to have a class on the evening or afternoon. So I expect today probably we will have more students than the one on the Monday morning, because this should be the time that everyone should be available. That's how I found from this suggestion. But anyway, it doesn't matter because I know everyone's busy. That I know nowadays we change to the 16-week, and then I start to heard about that if you have many classes in this semester, usually, for example, the undergraduate or the first year of a master student, because then you have many courses, and then every course you want to finish with 16 weeks. I believe at this moment, every one of you should be very busy. So you're probably after the middle of the semester, you are in the nightmares of the homework exam with all of the subject, because every courses has to finish by 16 weeks. So it's fine that because as I say that I will record the classes, so it doesn't matter that you will be joining or not. But also it would be good that then the viewer on my YouTube is higher, because most of you did not present physically today. So then we won't have a class today, next week, as we already mentioned. But unfortunately, I also cannot make it because there's some duty I have to join on Monday. So last time I already mentioned we have a makeup class, but I make a mistake to put the wrong date. That should be the May 21 rather than May 28. If you look at the previous upload slides, May 28, but that's actually the mistake. So I decided to shift this one to this. So 2 days ago, this is option, but today it's become not option anymore. But still, you feel free to join. And then I plan to finish the midterm grading in this week, but considering the Wednesday afternoon, Wednesday evening class, I expect that not everyone can come. But once I give you back for the midterm, I believe you will have so many questions want to check. So I think it will be good. We will use this timing that to announce the midterm results and then help you with provide some basic solution that you know that what would be typical, like how to address for each questions. And then as a target, we will still have the exam on the May 29. And one more thing, just in the case, because we need to spend probably half class to explain the midterm and provide you have the chance to discuss if there's some mistake or not. So probably there will be the one situation that we might not have enough time to talk about the junction field effect transistor. But it's fine. This will not be included in the final exam. In the last several years, I never included any of the question for the junction FET. So either I can provide you, if you are interested, I will still upload the slide and you can look up. It's just not a big slide, just I think in less than 10, probably less than 15 slides. And then you can read the slide by yourself if you are interested in. And then also I can share the last year, the recording that we also talk about the junction FET. That's in case if we cannot make it. But in anyhow, the junction FET will not include in the final exam. Okay, so that will be the end of the announcement. So that will be the end of this class. So if you have any question, just let me know. So we will see each other on this day again. Okay.